Okay, so welcome back, everybody. Hope everyone had a good spring break. Quick reminder before we get back into the math, don't forget we have an exam on Wednesday, so it's coming up real quick here. So I hope you found a little bit of time during spring break, perhaps, to flip through, kind of keep your Math 216 skills, polished. So anyway, so here we go. So here's what we were talking about last time. We were talking about how you can define an algebra of linear transformations. Specifically, there's certain kinds of linear transformations that we're doing a lot with in solving differential equations. The derivative can be thought of, the act of differentiation can be thought of as a linear transformation. The multiplication by some coefficient function can be thought of as a linear transformation. So really, everything that you do on the left side of a differential equation can be thought of as a linear transformation in that algebra, and that algebra has most of the properties of algebra that you remember from high school. It's a pretty surprising result, really. It seems suspiciously weird that this would be the case, but it does work out very nicely. Keep in mind, you've got to worry about stuff like commutativity, right? Multiplication of linear transformations is not always commutative, but it is for these, right? So very, very nice. So some important consequences came out from these observations. We weren't quite done talking about those, so let's finish that up before we go on to 5.3. The first consequence I like to point out is just one of motivation, but if you rewrite L in its new, factored polynomial form, right? And then shuffle things around, we observe that you can rewrite L, in fact, like this, and therefore we can understand this great big nasty nth order differential equation by the smart alecky observation of, hey, by the way, if I can make this 0, in other words, if I can solve that differential equation, we're good, right? And that differential equation is easy to solve. That differential equation is the natural growth equation, whose solutions we already know. Right, so I think this is a pretty big thought. Back in chapter 4, we tried exponentials with no motivation. I just kind of said, hey, let's try this. Hey, maybe we'll get lucky. What do you suppose is going to happen if we try this? And we did. We got super lucky, and it worked, and that's great. But that's kind of pulling things out of thin air. Here, we have a motivation, right? Absent that extremely lucky guess, here is a motivation for why we should have tried exponentials. So that's a pretty cool point, I think. Next thing we talked about, little algebraic preliminary here, but we're going to give a justification of another theorem from chapter 4. Algebraic preliminary is to see what d minus r does to functions that look like this. The answer is d minus r takes functions that look like that and produces, functions that looks kind of the same. With two slight edits, the power of x goes down by 1, and there's some constant out front. Okay. So a shorthand way to say this is that what d minus r does to functions of this form is it kills one copy of x. That's a sort of a shorthand way of thinking about that. So with that in mind, here's the situation that we were considering back in 4.2. What if your characteristic polynomial, that we now understand as being really just part of L, what if that characteristic polynomial has inside of it a repeated root? Right? So in other words, what if there's a factor of d minus r that's repeated m different times in the multiplicity? Well, we made this assertion that, okay, well then these are the solutions for, certain values of k. We pulled that out of thin air. Not only did I not motivate that, I never even proved it. Right? At least with the exponentials business, we eventually did prove that they work in those cases, right? But this whole business about just throw in some extra factors of x, never proved it. So here's the easy proof, and I think we kind of rushed through this at the very end of last Friday's lecture. So, but let's go through this again now. Our L Right, L is now this factored polynomial in D. How do I know that these are solutions? Well, I'm going to just compute L of Y. Act L on Y. Here's L, there's my proposed Y. And recall, what we agreed above is that these copies of D minus R, each D minus R pretty much just kills a factor of X. And spacing out appropriately, why don't I do spacing out appropriately, taking our, let's spread out our D minus R's like that. Here's our Y. These D minus R's just kill those copies of X. Now, roughly speaking, I mean, details to follow. You have an exponential that results. You got to worry about this coefficient out front. It ends up being k factorial. It's about to get multiplied by 0, so who cares? But the big point here is that factors of D minus R, because they act to kill factors of X, the reason you put in these factors of X is because they are something that will allow these D minus R's to kind of go away. So there you go. There's the proof. Again, a couple additional details, but we do get down to 0, and therefore L of Y is equal to 0, and therefore these Y's are solutions to those differential equations. So again, back in chapter 4, we just waved our hands and said, we're going to have much more powerful tools later on, and we'll prove that these are solutions then. Now we have proved it, that those are the solutions. Okay. Alrighty. Okay, next thing that we never quite got around to proving back in chapter 4. There was this whole business about, what do you do with particular solutions, right? The section on undetermined coefficients. And there's a great big enormous theorem in there that looks a lot like this one that says if you're looking at one of these non-homogeneous equations, and if your right-hand side takes this, a form that looks something like that, and I remember it was different in chapter 4, but given a certain form for the right-hand side, we wrote down a plausible-looking, what I called at the time, naive guess for your particular solution. Looks something kind of like that. Talk about the differences in a moment. And then we further discussed that you take that naive guess and multiply by x to the m if R is a root of multiplicity m. If R is a root of multiplicity m of your characteristic polynomial. So we never really proved either part of this theorem. Never proved part 1, never proved part 2. I'm not going to talk about part 1 because I think part 1 is kind of plausible. I mean, part 1 is just a manifestation of what we saw work time and time and time again in the first few examples of section 4.3. So 1's pretty plausible, and we can prove it. It takes a while to kind of write it all down. It's just kind of tedious. That's not what this class is about. What we didn't do, and I think really need to do, is talk about what the motivation is for this extra factor of x to the m. Where does that come from? Right? Again, we just wrote it down, and I said, trust me, it works. Discussion to come later, and here we are. So, how is it in this case that throwing in some extra factors of x allow us to have a correct form for a particular solution when you have a root of multiplicity m in the characteristic polynomial? Now, before we go on, let me address the concern that you may have. Hey, this isn't the same theorem. This is supposed to have sines and cosines in it. What happened to the sines and cosines? Okay, here's a little subtle trick that I've pulled here. This r is a complex number. That's an a plus bi. And don't forget that e to the power of rx can be rewritten as linear combinations of exponential times cosine and exponential times sine. Right? So this function that's being considered here as a right-hand side is a linear combination of the kinds of functions that were being considered in section 4.3. And furthermore, went through the appropriate algebra way back when, but these functions individually that were the subject of the theorem in 4.3 can furthermore be written as linear combinations of these kinds of functions. So really, yes, it is a different theorem, but it's a very similar looking theorem. And in fact, these are considered to be equivalent theorems in the sense that you can use the chapter 4 theorem to prove this one by just making a linear combinations argument. And likewise, you can use this theorem to prove the chapter 4 theorem by making a linear combinations argument. So they're very kind of closely connected statements, and you prove one, you've effectively proved the other. I want to consider this one here because it's a little bit algebraically more easy to work with. The reason I didn't do this one in chapter 4 is these are, as you'll notice, complex valued functions, and in practice, day in and day out, when you're looking at real models of real situations, you're going to be dealing with real valued functions. So I think the relatability of the real version makes sense for chapter 4, and the algebraic convenience of this version makes sense for here in chapter 5. Okay, all right. So it remains. What's the deal with these extra factors of x to the m? And here's the argument. Don't forget, our L is really just a polynomial in D that factors like any other polynomial. So when we presume we have, that R has a multiplicity of M, all that's saying is that we have a factor of D minus R to the M, just like it was observed on the previous page. Why are we guessing? Let's see, let me go back up to, in this case, let me do it like this. D minus R to the M. Why are we guessing this as our Y? We ask. Specifically, why are we putting this factor of x to the m in there? And it's for very similar reasons as on the previous page. We've got these d minus r to the m's in here that are, messing things up. We put an extra m factors of x here so that these d minus r's can pair off and run away with these factors of x, disappearing, thus resulting in, all that's left over. Now, of course, there's some details. Every time d minus r cancels with an x, there is an ensuing extra factor of a constant. So these c constants in here, they're not the same as these d constants, but they're extra factors of, a few factors of, scalar numbers. And so punchline is these factors of x kill these d minus r's to result in this algebra down here. And the nice thing about this algebra is exactly the algebra that we have up here. This is that equation where r is not a root of the polynomial. Right? You can see the characteristic polynomial right here is just the q. This is just the part where all the d minus r's have already been pulled out. There are no factors of d minus r in here. R is not a root of this polynomial. This is exactly our naive guess. We already believe that this ought to work. And so then you just kind of back solve, knowing that you can solve this blue equation, knowing the d's, you can just work backwards and find the c's and make this equation work. Okay. So there's a lot of little details in there. Again, the point to this discussion is not to get lost in the details. The point is to the plausibility. What's the motivation for putting in a bunch of factors of x in here? The motivation is factors of x cancel with factors of d minus r inside of the characteristic polynomial. Okay, so again, I think that's a lot of details necessary to make that a rigorous proof, but I think this does make it plausible. And I think that's a valuable thing. Okay. Right. So moving along, we're going to now go on with section 5.3. By the way, section 5.3 is a long one. We're not going to come close to finishing it today. In fact, we're also probably not going to finish it in our next lecture. Friday, I guess it will be, because of course we have exam Wednesday. It's a long section. I think it's probably going to take us pushing 3 lectures to get this all done. Okay, so I want to start off with a reminder. We saw back in section 5.1 that if you write down a function that looks like this, in other words, if you interpret a matrix as a function, that function is a linear transformation from Rn to Rm. Now, that's easy to prove. I gave that to y'all as an exercise back in section 5.1. You just put in a linear combination in, confirm that you get the appropriate linear combination out. Okay. All that shows is that the arrow goes this way. If you give me a matrix, it is a linear transformation. What I'm going to show you now is that actually this goes both ways. If you give me a linear transformation from Rn to Rm, any linear transformation from Rn to Rm, I'm going to show that that can be represented with a matrix. That's what this theorem here says. Given a linear transformation from Rn to Rm, then there is some sort of a matrix A that computes T by way of that formula. Okay. This is arguably a harder proof than what we did previously. I mean, the first version, the going this way with it, it's just a matter of checking the linearity condition. The thing that makes this second part hard is that I'm claiming that something exists, right, with no suggestion in the statement of where to find it. Right, so we've there's a tricky task in front of us. The way we're going to prove that this thing exists is a pretty straightforward method. We're going to prove that it exists by finding it. This matrix A. Here's how I know it exists. There it is, defined by that. Now I've got to prove that this has the required properties, but I'm going to define as my matrix A that I claim represents this linear transformation as a matrix whose columns are just T of the standard basis vectors in the domain. I claim that's going to work. So by work, keep in mind what I'm claiming. I'm claiming that this matrix will allow me to compute the linear transformation by just multiplication. Okay, this is a plug and chug confirmation at this point. Here's the calculation. Given this matrix A, the way I multiply A times some vector is, well, I take the columns and do the appropriate linear combinations. Right. Section 1.2, way back when. As y'all recall, this is one of my 2 favorite points of view on matrix multiplication. Forget that whole dot product, row dot column thing. Don't forget it, but back burner that row dot column thing. Think of matrix multiplications as linear combinations of columns in this case. Okay. Right. By our choice, by construction, these A's are the images of the standard basis vectors. Okay. T of E1 through T of En. That was our choice. Now, don't forget we're talking about a linear transformation here. T is a linear transformation, and therefore we get to use the linearity property. Note that I have here a linear combination of output vectors. Linear combinations of outputs come from, well, the same linear combination of the inputs. So I can rewrite that as that. And lo and behold, this linear combination of the standard basis vectors with coefficients being the coordinates of x, that is x. That's where this x came from. X is has coordinates x1 through xn. And as required, t of x is ax. Okay, so there's that proof. I think this is a really nice proof. It's makes use of a lot of things that we've talked about. It makes use of our sort of new interpretation of matrix multiplication, and it makes use of linearity, but in a very streamlined and crisp kind of way, right? There's not a lot of excess fat on this. This is a very tight proof. And again, a surprising, kind of surprising result in that linear transformations from Rn to Rm are exactly matrix functions. Every one of these is one of those. Every one of those is one of these. Let me take a quick pause for questions. Anybody have any questions about this? Okay. All right. Okay. All right, let me show you an example of how to use this. I'm going to start off by observing that rotations in R2 around the origin are linear transformations. And before we get into the calculations of this example, I want to give you a kind of a plausibility argument on that. So let's talk about rotations. Here's R2. A linear transformation would have the property that if I take any two vectors and if I add them, and then rotate, then I get the same result as if I were to take these two vectors, rotate them, and then add. And the plausibility argument I'm going to give on that is, let's draw the corresponding parallelogram. Oh, that's terrible. Let's try that again. One more time. Close enough. Okay, so let's take that parallelogram. Let me just rotate that parallelogram now by some arbitrary amount. And now let's just kind of talk through, okay, well, if I take these two vectors, if I take those two vectors, add, and then rotate, I get that point. Whereas, clean this off a little bit, sorry. If I were to instead rotate the vectors first, and then add, well, I get the same point. So the argument here is just a appeal to geometry. If you rotate a parallelogram, you get another parallelogram, and add and then rotate, and then add are both of those processes take place on this same picture of parallelograms. So we have this commutes with addition property. And likewise with scaling, easy to argue that if you scale and then rotate, that's the same as rotating and then scaling. So anyway, it's a nice observation to make. Rotations are linear transformations. Having made this observation that rotations around the origin are linear transformations, we can actually use that as a computational tool. A little counterintuitive. It seems like we're making some abstract observation about rotations, but keep in mind, being a linear transformation is a very powerful condition. There are very few functions that are linear transformations. There are so few functions that are linear transformations that if you just tell me what it does to a couple of them, I can rule out all the other possibilities, and here's the only remaining function. Right? We talked about that a while ago. So let's capitalize in that way on this. Simply knowing that it's a rotation, I can make an easy geometry argument that E1, when I rotate E1, I get this vector here, R of E1, whose formula is easy to write down. That's a little trig exercise, right? Think back to trig class. This vector of length 1 and at some angle theta counterclockwise off of the horizontal, sines and cosines. Right? So, easy. On the other hand, E2, here's E2. Here's what you get when you rotate E2. You get that. It's another little trig exercise, right? You've got to remind yourself and think about, so we've got this triangle here, and that angle is theta. Be careful, we're talking about that angle, not this whole angle here. Right? Just that angle is theta. And so play trig games with the triangle, and not hard to persuade yourself. Negative sine theta, cosine theta. And then it's pretty much all over. The images of the standard basis vectors give you the columns. And there's your matrix. Really counterintuitive and surprising fact, but if you want to rotate any vector in R2, you want to rotate it by some angle, not only is that perfectly doable, it's perfectly doable with a really easy formula involving a matrix. So, really nice conclusion, and again, I emphasize, where did this conclude? What was the critical thing that made this all possible is the observation in the first place that rotations are linear transformations. How we doing? Everybody on board? All right. Okay. A little memory tool. I like this a lot. I think this is a good thing for you all to keep in mind. If you want to think about the relation between linear transformations and matrices, and what we see here is that, with when you're talking about Rn to Rm, linear transformations and matrices are in perfect correspondence. If you give me a transformation, there's a corresponding matrix. And if you give me a matrix, there is a corresponding transformation. So they pair up perfectly. It's kind of like it's almost like they're the same thing. They're different in that they are, they're written down in different ways, but they pair up perfectly. And you can think of either one as representing the other one. The way they relate, the way this bijection works, is that the columns of the matrix are the images of the standard basis vectors. That's what this equation says right here. The columns are the images of the standard basis vector. So I have that written down over here. This applies for all linear transformations from Rn to Rm. The columns are the images of the standard basis vectors. So please drill that into your heads. Make sure that you're really, really crisply comfortable with that. This is useful in a lot of different ways. If you have a matrix given to you, hey, the columns of that matrix are the images of the corresponding standard basis vectors. Right? So you can interpret this in a lot of different contexts. Okay. All right. Now this does bring up an awkwardness, though. This correspondence. So, we've just got through observing that if you in this context, Rn to Rm, if you give me a linear transformation, there is a corresponding matrix, and if you give me a matrix, then there's a corresponding linear transformation. Here's the awkwardness. We just got through defining a multiplication on linear transformations, right? There's that whole thing with compositions back in early 5.2. So we've got a multiplication on linear transformations. Way back when, we defined a multiplication on matrices, which y'all have all seen many times, and we haven't exactly motivated it yet, but nevertheless, we have that formula. Okay? So we've got a multiplication on linear transformations, we've got a multiplication on matrices, and now we just made the observation that, in this context, linear transformations and matrices are kind of the same thing. They're certainly very closely connected. So we've got now, instead of two multiplications in different contexts, now we've kind of got arguably two multiplications in this overlapping sort of kind of the same context. So the big worry that we have to worry about right now is, what if those two different multiplications are different? right? What if when you multiply in the sense of matrices, the corresponding linear transformation is different than if you had multiplied in the sense of linear transformation? Wouldn't that be annoying? So the way we've approached this situation, we have a legitimate worry that might be the case. Here's the good news. The answer is it's fine. It corresponds nicely. If you multiply two linear transformations in the sense of composing, the way we define multiplication for linear transformations, the resulting matrix is the multiplication of the two individual matrices representing the transformations individually. So linear transformation multiplication corresponds perfectly to matrix multiplication, which is a big sigh of relief. Now we don't have to worry about the algebraic nightmares that would assume, and instead we get algebraic convenience. I'm going to show you one nice application of this. Here's another theorem that I never really quite got around to proving long ago, and that is associativity of matrix multiplication. So this is a long time ago. This goes all the way back to section 1.2, very start of the semester. I asserted it. We've used it quite a bit. We never did prove it. Now the book did. The book has in it a perfectly fine proof that matrix multiplication is associative. The book's proof is, however, I think from an intuitive standpoint, very opaque. They write down the formula involving sigmas, and they write down, what happens if you multiply and then multiply again, and they have all these sigmas and subscripts and i's and j's and k's and move things around, all perfectly legitimate, and out comes a big thumbs up that, yeah, it works. But it's just kind of symbols moving around on the page, and there's no sort of satisfaction of intuition in, why should this be true? Do I feel like this ought to be true? I'm going to give you what I think now is a very satisfying proof of that matrix multiplication is associative. We just got through discussing that matrix multiplication corresponds perfectly with linear transformation multiplication. So rather than prove this fact, using matrix multiplication, it's kind of unwieldy and hard to work with, I am instead just going to prove the associativity of multiplication of linear transformations. In other words, I'm just going to prove the associativity of composing functions. And this is super easy. It's super easy. Look how easy this is. R times st as a function that acts on some input vector x by, let's see here, we've got a bunch of compositions. The first thing we're going to do is compose s and t, and then having done that, we're going to pre-compose with r, and altogether what we're going to get is r of s of t of x. I hope that's the right number of parentheses. I think so. Okay. On the other hand, what is rs t of x? Well, here we're going to compose rs and then compose t, thus giving us r of s of t of x. And these are clearly the same. I mean, here's another way to say it. Another way to say this is, if you take some input vector x and do t to it, and then do s and then do r, that's the same as taking that same input vector x and first doing t and then doing s and then doing r. The only difference is where's the dramatic pause. It's the exact same calculation, it's the exact same process. So composition of functions is, I'm going to say, obviously associative, right? It's such an easy argument, it's just a one-liner to write down. And because this is obviously associative, because linear transformation algebra products correspond to matrix products, it follows that this really ought to be associative. What do y'all think about that? Anybody have any questions? I find this argument to be much more satisfying than the book's sigma argument back in section 1.2. I encourage you to flip back and take a look at that argument in section 1.2. Again, it's highly rigorous. It's pretty unsatisfying. I like this one a lot better. Okay, so we're going to move on now to things that we can do with bases. And it turns out there's some really powerful things that we can do here. This is by the way, this is arguably the beginning of a very long arc. We're going to be doing things with using bases to rewrite things in coordinates, to rewrite things with as matrices, and ultimately we're going to use what we're starting here as a tool for solving differential equations. This is our sort of second big arc of solving differential equations with linear algebra. The first one, recall, we started talking about linear combinations and linear independence, and that allowed us to define vector spaces and subspaces, and eventually the idea of dimension and linearity were essential tools in solving linear constant coefficient differential equations. Right? There's something kind of analogous that's kind of starting now. So anyway, it's a very important part of the course. So first a flashback. We'll talk about bases. Remember, if you have a basis, let me do this in purple. If you have a basis for a vector space, there is a unique way to write any other vector. If you give me any other vector v, there's a unique way to write that vector v as a linear combination of those basis vectors. Right? There's a uniqueness of representation. And you have to have a basis for this to be true. Okay. So there's exactly one way to write down these coordinates, coefficients C1 through Cn, and we call those coordinates. Okay, I hope everybody remembers this. This goes all the way back to section 2.4. Okay, so these are, unique. So in fact, we've developed a notation for this. The basis allows you to write a vector in terms of its coordinates. Okay, and let's talk again about the advantage. Why would I want to do this? Isn't this a bunch of trouble? Why can't I just talk about the vector as is? Perfectly good vector, right? Look how easy it is to write that down, just v, right? Well, if I need to do some sort of manipulations, if I need to do some sort of business with v, well, this might actually, inside of this single letter name that I've given to it, this might actually be a pretty ugly thing. It might be a 5x7 matrix. Or it might be some great big nasty function that involves exponentials and sines and cosines and stuff. Right? It could be kind of a monster, conceivably. What's nice about this coordinates idea is that no matter how monstrous the vector is, if you've picked a basis, v, script v here, the coordinates of that vector with respect to that basis are always just a list of numbers. Said differently, it's a way of saying whatever outrageously weird vector space we might be doing business in, we can effectively kind of pretend like we're back in Rn and just dealing with lists of numbers. And that's really nice. Okay, does everybody remember all that stuff? Okay. So now a couple of different points of view on this. I like to think of, let me write it this way first. Okay, so you can think of then a basis as a function. And it's a little bit of a weird point of view. We typically think of a basis as being, as described, a basis is a list of vectors. That's independent and spans the vector space, right? So we think of it as a list of vectors. Let's think of it as a function because it allows you to take a vector in the vector space, and then it returns to you a list of coordinates that I can think of as being an Rn. So a vector is a function. It gives you give me an input, I give you an output. The input's a vector in a vector space. The output is an ordered n-tuple. In fact, this you can think of this function as going the other way as well, because, of course, if you give me a list of coordinates, well, I can find the corresponding vector. In other words, there is exactly one vector whose coordinates are those numbers. So you can think of a function going the other way as well. The notations that we're going to use, I'm going to borrow the book's choice here. Thinking of the basis as being a function this way, we're going to use the book's notation of square brackets with a subscript being the name of the basis. So that the square brackets with a subscript means whatever's on the inside is a vector, and I want you to write the list of coordinates. The book does not have a notation for going the other way. It didn't write anything down, and in a few instances it's really convenient to actually have a notation for going the other way. So I just put a subscript on the other side. I think that's pretty plausible, right? So if you see me write a subscript on the left instead of the right, that means don't think of this as a vector that I'm converting into coordinates. Think of this as I started with a list of coordinates, and this is the corresponding vector. All right, how are we doing? Pause for questions. Okay. All right. Here's a different point of view. You won't find this in the book. I think this is really valuable. This is how I think about these things, and I think it's useful. You can think of the basis as being kind of like a language. And hear me out. But I think the analogy is actually quite strong. What is a language? A language is a way of saying, look, there are these different things we're going to want to talk about, like this thing. I might want to talk about this thing. But when I talk about this, I don't want to have to say, this piece of plastic that's about this long and about that wide and it has the buttons on it, and when you press certain buttons, certain things happen. Right? That is inconvenient. It's so much nicer to take this hard to talk about thing and just put a label on it and say, let's just call this remote control. Right? So remote control is an easy label. I can say it quickly. I can remember it. I can write it down with letters. Much easier than drawing a picture, right, of a thing. Right? And there's all sorts of similar examples. Cable. It'd be hard to describe this thing with the word table. Easy. Okay, so in fact, that's really what a basis is doing here. If you think about it, a basis is a thing that allows you to take potentially hard to talk about things, vectors and vector spaces at this point, and put convenient, easily used, easily discussed labels on them. It's really very much like a language in that sense. So I use this little metaphor quite a bit. So rather than saying, strictly speaking, I should describe these numbers here as the coordinates of the vector v with respect to the basis script v. And instead, I will sometimes say, thinking of the vector v in script v language. Okay? So that's just my, taking advantage of this metaphor. That's a shorthand way to describe coordinates. Okay. Oh, yeah. Here's another observation. Let's go back up here. Given a basis, right? Given a bunch of these vectors, and given a vector in the vector space in question, we get corresponding coordinates. Well, no surprise, what the coordinates are depend on the basis. So I hope it seems plausible, but if you change these basis vectors, if you pick a different basis instead of the basis you started with, well, of course you're going to get different coefficients in this linear combinations, and therefore you'll get different coordinates. So let's go down here and think about that in the language context. If you use a different basis, you get different coordinates. In the language metaphor, if you are speaking a different language, the name that you apply to things is, of course, different. Right? So in English, this is table, but in French, it's something else. If it's in Portuguese, it's something else. Right? Same thing. We're still talking about a table, right? But in different languages, it would have a different convenient label. Again, the analogy with languages is kind of perfect. Every basis can be thought of as a language. Change the basis, of course, you get different labels. Okay. All right. So I'm a big fan of that point of view on thinking of a basis as a language in this context. Okay. A couple of quick examples. So here's a vector space. The collection of at most quadratic polynomials. We've done stuff in this vector space before. I'm going to assert that this is a basis. Here let me circle. I'm going to assert that that is a basis. Now that's something y'all know how to check. Okay. And so let's consider that basis as the basis that we're going to work with for the purposes of this example. Let's consider now this vector here, f. There is a way to write that vector f, inconvenient, clunky function thing that it is. I can write that as a linear combination of these basis vectors, v1, v2, and v3. And of course, you got to work out. There's a little system of equations that will allow you to identify what that is. And with some effort, you can find that those coefficients are 3, 3, and 11, and therefore those are the coordinates of that vector with respect to that basis. Okay. So, convenient, compact, familiar notation here to talk about what otherwise would be a function, which is sometimes inconvenient. But 3, 3, 11, very familiar, very convenient, very compact. Okay. All right, another quick example. This next example is going to look a little easier. It's actually a little harder. What makes this example harder is that the vector space that we're going to be looking inside of, being as it is R3, now again, that seems easier. R3, it's good old R3, right? But so the vectors, the abstract vectors that we're going to be trying to describe here, cosmetically look just like the lists of coordinates that we're going to represent them with. So there's sort of a you don't have the convenience of type to help you keep track of what kinds of things you're dealing with. So nevertheless, here is how you can do the same sort of thing. Suppose you have the following basis for R3, and suppose you want to write this vector, for example, in coordinates with respect to this basis. Well, system of equations, compute, and outcome these numbers as the appropriate coefficients. Therefore, those are the coordinates of that vector with respect to that basis. Or, same statement, effectively, this vector is the 4, -2, 1 linear combination of those basis vectors. So this is like a kind of a passive tense, active tense thing going on here between what this is saying. If you start with a vector and say, hey, with respect to this basis, what are the coordinates? Here they are. On the other hand, if you start with the coordinates, what do these coordinates represent with respect to this basis? Here's the vector. Both of these statements are just saying this. All right. Good stopping point. We'll call it a day here. See y'all later. Good luck on the test on Wednesday.